of it. So I'm like, why are you here? Because I lived out in the sticks. I mean, makes St. Helens look like a big town, literally. And I went, what? So I really liked the guy a lot. I had 3 classes. The only guy in high school who I A, respected, and B, made me work hard in class. But I remember one day he just goes, for God's sakes, Jay, just look at it, find an equation that fits what you need. I'm like, oh. And it wasn't until much later that the relationship aspect of it hit me. I was like, wait a minute, we're accelerating. I feel like that is literally the definition of acceleration is A equals, and I went that way. But you do what you do. If you have to at first, dink around this way, knock yourself out. I also asked him one time, who in their right mind would teach high school math and physics? What is wrong with you? Anyway, I called him about 15 years ago and said, I'm sorry about that. Yeah, so whatever. But it's crazy stuff. Now, here we go. I feel like we know this. We don't know this. We do know this. And we know this. So our answer is 60 watts. There we go. Nice. Now, what did I want to know total? What did I ask for? How far does he, no, what is his total displacement in that time? Which, by the way, is also the last question I asked. So I don't know why I asked it twice. What was his last displacement? Well, I don't know. I feel like it's 1/2. A, why are you using that equation? Well, let's think about it for a minute. Now, I want to know this guy. I don't think his final velocity has a lot to do with it now, but I have him, and I've got that. And this formula does it. And then you're like, plus he doesn't have an initial velocity. That's right. So it's 0 times 15, whatever. Now I heard someone said, do I times first, do I exponentize first, for God's sakes? Please excuse my dear Aunt Sally. This is 2. This is 225. The answer is 450 meters. Yes? Right? Now, how is it really that much different, Mr. Groom, if I'm doing for the first 3 seconds? It's not a lot different at all, right? So in the first 3 seconds, it's 18, is that right?
Yes.
In 6 seconds, 72. In 9, it is 162. 12, it's 288.
Oh, that's 15.
Oh my God, it's right there. Okay. Now, the reason I do that is because back in the day, Fuse and Shush, thanks. Back in the day, I had a hard time with this next thing I'm going to show you. I don't know what my problem was. Probably I didn't pay attention. That was part of it. But the other part of it is, I don't know, I guess it just never really hit me as to like how weird and cool that was. Oops. So I can keep track of time and then where we are. What was that one? 18.
70, you put 19.
I hate you too. All right, 72?
162. 288. 450.
Oh.
That's a big one. You really accelerated through that.
Okay. So, I'm doing this today because I want to show you something, but I also want to show you that when we're doing our labs, I want to be using a lot of tables in Excel. We're going to do a lot more of that as we go along. Okay? If you are a person that likes to use, I don't care if you want to use GeoGebra, I don't care if you use Desmos, but we're going to look for the graphs. Right? You're going to have data points, I want to see them graph. I personally would use Excel, you knock yourself out. Let me use Google Sheets. When to go for it, I don't care. Okay? There it is. Hey, that's not a straight line. That's not a straight line. Yes?
I was going to say it's exponential.
It's not exponential. Got another idea?
It's that thing.
It is quadratic.
Oh, yeah.
Oh.
Sure, how do I know it's quadratic? Well, look at the form, look at the equation you used to get this data. What equation did you use to get this data? It's a quadratic. Was it not? It was 1/2 AT squared. That's it. Isn't that beautiful? Now, you're like, wait a minute. Are you telling me that I could have the computer find an equation for this thing? I can. If you click on add a trend line right here, maybe, and then if you put it on polynomial, second order polynomial, which means quadratic, you can literally find the equation. You shut up right now. Y equals 2x squared plus, or minus, I should say, e minus 13 is another way of saying 0 for the calculator. So it's really y equals 2x squared. Well, what's my x? My x is time, yes? Isn't that the equation we used? Y equals 2t squared. Isn't that what we did? Well, I'm sorry, it was x equals 2t squared. Yes. Mr. Green, what does this mean r squared is 1? It means it's freaking perfect. That's what it means. Okay. That make sense? Yes? Now, this is where we're going to do a little math because, well, math is awesome. I'm going to move this guy out of the way. Let's just go, if you don't mind. Okay. Now, if you come over here and you said, all right, well, initially, of course, we're going 0. I'm going to do this. I'm going to add an extra equation in here. This was time. Obviously, displacement. And velocity. Cool. Obviously, it was going 0 initially, yes? How fast was he going at the end of 3 seconds? At the end of 3 seconds, how fast was he going? Now, Mr. Grum. What's that? 12 meters. How did you get that?
4 meters a second.
He was accelerating at 4 meters a second.
Times 3 seconds.
Times 3 is 12. Beautiful. What about 6? 24. 36. Oh my God, it could be 48. It is. 60. What? Now, watch me. Control. And then insert scatter plot. Ba-boom. Oh, it's a straight line. I am not shocked by this.
Acceleration is constant.
So, the constant velocity means that what?
Constant.
Constant acceleration. Well, looky there. Give it to me. Go away. There. Oh, look at that. It's y. It's v equals 4t in essence, yes? Golly, I'm not shocked by this. Wait, there's more. Mr. Groom. The acceleration here. Now, you already know the acceleration is what? 4. How could you figure that out? I feel like you could say equals, wait for it, the velocity minus the velocity, right? Divided by the time, which of course was 3 seconds, correct? And then a person could drag this baby down. Oh, it's 4. Now, because I'm a boring person, I'm going to go ahead and graph it because, well, that's what I do. And I can then insert another scatter plot, and it's like, oh, geez, it's flat. How about that? Okay. So, first thing I want to talk about today is really this. Okay? And we've talked about it a little bit, but I want to make sure this is clear in your head. Under constant non-zero acceleration, displacement versus time, quadratic. It's quadratic. Velocity versus time, linear. Acceleration versus time, constant. That's just what we looked at when we graphed it. Okay? You got those data points. We stuck them in. We looked at the graph. Hey, that ain't linear. What is it? Oh, Jesus, quadratic. Not surprisingly, because that's where I got the data from. Was a quadratic. Huh? That's a big deal. To quote my favorite former vice president, Joe Biden, the walking goof machine, it's a big effing deal. Huh. Except he didn't say effing. He actually used the real word. That's class. That is class. That's how you know when you got class, when your vice president's saying, this is a big effing deal. On the mic. That's awesome. That was my favorite. By Shotgun was one of my all-time favorites. His class. I missed the guy already. I miss him saying goofy things. It was awesome. What's he going to say today? What's he going to say today? Oh, mercy. Ever got that? Yeah? Ooh, look at you drawing the pretty pictures on the computer. Yours are pretty too. It's good. Oh, stop. Yeah. All right, now, how about this one? With zero acceleration. What am I saying? Yeah. There you go. Mr. Green, are you going to say both? No, I'll probably say one or the other. If you hear constant velocity, zero acceleration. If it's zero acceleration, it's constant velocity. Same thing. Two sides, if you will. Same coin. So let's look at that. Let's start down here with acceleration. Acceleration versus time. I can't see it. That's because it's on the axis, yo. It's zero. Talk to me about velocity. Velocity versus time. What is it? Well, it's literally constant, so voila. Well, then what would my displacement look like? Linear. That's right. Boom. Displacement. Time. Linear. For those of you who are calculus inclined, you will find later this year when we do derivatives, the derivative or the change in a quadratic is a linear function. And the derivative or the change in a linear function is a constant function. And this is one everybody can do right now. How fast is a constant changing?
Exactly.
It is. And so the derivative or the change in a constant, how fast is it changing? It's not changing. That's why it's zero. All the way down the line. Okay? So keep that in mind as we do these this year. That's going to show up all the time. Okay? Now, that's part of what I want to talk about today. There's three things I want to talk about. But I'm going to do one more thing with the data we had earlier. Now, here's my question to you. How far, this is kind of big, did the car go in the first 3 seconds? You're like, I already know that. I know. Ditto, 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 ditto. Second 3 seconds. Well, it's just ditto again, I guess. There you go. Third 3 second interval. Ditto, 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 ditto. I'll screw that. Fourth and fifth second intervals. 3 second intervals. Okay? How would I know that, Mr. Groom? It's a great question. So, a moment ago, we had 0 and 0. We had, after 3, we were where? At 18, is that right?
Yeah.
And then 6 was 72. And 9 was 162. And 12 was 288. And 15 was 450. Yes? So, my question is this, simply. How far did we go here? 18. Right? How far did we go between here and here? There you go. I think that's not very hard, right? What's that?
I was like going to use like equations, but then that's really easy.
No, this is just minus. This is where I was, this is where I am now. Ooh, done. Now, hold up. This is exciting. What were you going to say? Are you telling me there's a freaking pattern here? There is a freaking pattern here. Now, you may remember this from Algebra 2 or Pre-Calculus or wherever when you talked about this. We call this column the first difference. Ah, you hooker. We call this the first difference. That is, this is the first time we subtracted things, yes? First difference. The first difference is not a constant. It's not at all this time. If it was a constant, we would say the function was a linear function, right? Because to buy like one hamburger is this much, to buy two hamburgers is this much, three and so on. Every time you minus it, it'd be the same difference between them. That's literally the definition of a linear function. But that's not true here. But the second difference is a constant, yes? Am I right? You acting like I'm not right. Am I right? I feel like I'm right. The second difference is a constant. And because it is, in math class we would talk about, because this is true, we know that we have a quadratic relationship. Which doesn't shock me at all. At all. I'm thinking, oh yeah, I suppose that makes sense, because I knew it was quadratic to start with. But from a math class, we would just look at these relationships and we go, literally in a math class, you would see these numbers. 0, 18, 72, 162, 288, 450. Find a pattern. And you'd go, well, is it plus 2? It's not plus 2. And you'd dinkle fart around with it. And then the teacher would go, well, what if you minus? And you'd minus all these guys and you get this and you get this and so forth. And in math class, we would talk about how this, can you stop that? Thanks. And so because the first difference is not a constant, but in fact it's linear, that means that the second difference will be a constant, and it is. So because this is a second difference is a constant, what we would say is this. Because this is true, we know it's going to be sum y equals ax squared plus bx plus c. And that's how we talk about in a math classroom, okay? In this, this is not a math class, but the same relationships hold. What were you going to say?
If you go to like the third and fourth, would it be like a cubic and then?
Yes. Yes. Yes, 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 and yes. Beautiful. Now, question. It's a great question. I know what you're going to say. Mr. Groom, these are how far I went in the first 3 seconds, and the next 3, and the next 3, and the next 3, and the next 3. That's the numbers I want to look at. Okay? But let's look at these for a minute. What can you say about this? In the first 3 seconds, I went 18 meters, yes? In the next 3 seconds, I went 54 meters. How many more times how much further did I travel, times-wise? Yeah.
3 times.
So I went 3 times further in the second 3-second interval than first 3-second interval. Why is that? Because you're accelerating. That's right. It's because you're accelerating. But Mr. Groom, is there a relationship between here and here? There is. It's 5 times further. Right? 18 goes into 95 times. That's right. And what about here, Mr. Groom? I think it's 7. Am I right? 18 goes into 126? Yeah. And 18 goes into 162. If you were a betting man, you'd say 9 times, and you're right. Nice. And again, why? Because we are accelerating. So keep that in mind. That is why. Again, if it was nice and linear, you'd be going the same amount between each of them. Boring. But we're not. We are accelerating. So we are picking up speed as we go. We're going a lot. Why aren't you moving? Why do you hate me? Freaking copier hates me. I went to copy something this morning. It plugged up. You're like, well, that's not new. No, you're right. It's not new. But then guess what? Patterson's stuff was printing. So I'm like, I'm just going to jump ahead of his stuff. Oh, so I clean the machine out first. Then it starts printing, and it's printing Patterson stuff. I'm like, I'm just going to skip over his. As soon as I start printing mine, it clogs up. What? So I unclog it again, and then I jump over his stuff again, and guess what happens? Oh, yeah, it plugs up again. Hates me. Anyway, I don't care. I hate her too, but that's fine. So there is the chart again. The idea being is we're picking up more speed as we go along. we're going to be covering a lot more ground percentage-wise or multiplied-wise as we go through it. Now, what I'm going to set up for the rest of the day is this. Tomorrow, we're going to be having our first lab. Primarily, it's going to be collecting data tomorrow. So, I have a video that's on my website that I will make more prominent. It'll be on the physics page, linked on there. Watch this video or something. So that after you see how to run this program, it's called Physics Tracker. It's very easy. It's a free program. Listen, it's very easy. And yet, kids will be like, that's hard. It's not hard. You just have to dink with it a little bit. But it's free. If I paid $1 million, I'd want it to work a lot faster, better. I'd want to do it for me, is what I'd like it to do. Thank you very much. But it's free, so whatever. Okay? Now, the idea is tomorrow you're going to take your cell phone device. You're going to stand over yonder with your cell phone. There's a little camera, a little button, whatever. And your friend is going to walk thusly. You're not going to move. You're just going to stand there. Don't pan with them. It throws everything off. So hold it right there, and you're going to see the person walk across your camera. Slicker and a whistle. Now, in the background, you will put a meter stick on the wall. Does it matter which? No. As long as I can see it. Okay? That is for reference. Otherwise, the math we get will be in pixels per second, which is worse than useless. But because I have this meter stick in the background, I can actually correlate it to meters per second when it's done. Okay? Awesome. Now, you're going to tell your friend, go! And then your friend is going to wander through the first one at a constant velocity. Right? And when you use the physics tracker, you're expecting to see these kind of graphs. No acceleration? But Mr. Groom, it actually does this on the screen I see. Oh, does it? That's because your friend wobbles when she walks. Good for you. By the way, in the past, didn't use physics tracker. I used to use these motion detectors, and some people tend to, really give it some of this action when they walk. And oh my God, horrible. Okay. Some people really, the back does this business, and so you like put it up there and their head bobbing and weaving, and just so you put it on their butt, but then people will really shake their fannies. Okay, but this is better because it's just a picture, and in general, it's just wandering across the screen, and there they go, and it's pretty good. But this is not a actual observed amount. This is a calculated value, so it kind of wobbles up and down a little bit. Not a problem. In general, what's it doing? It's hugging the 0 line. Then you're going to look at the velocity. The computer program will actually give you this. Now, this really blows people away because there is a forward and a negative direction. This actually might be that, Mr. Groom, according to my graph, it had a negative velocity. It just means you're going backwards is all. Backwards, wherever that is. Yes? Don't panic. Nobody cares. Nobody cares. Yeah, but you're like, it isn't exact. It's like this. Again, it's not a calculated, it's a calculated value, not an actual measured value. Because what it's actually measuring is your position over time. And so it'll be something like this. And it should be, linear. But there's little humps and bumps in this deal too. And you're like, what? Because these little humps and bumps, that's where these little humps and bumps come from. Okay? But it should be like, oh yeah. You're going to watch the video. In the video, I will show you how to do this. It'll actually give you equations for each of these guys. Okay? That's the trickiest part. Well, that's not the trickiest part. The trickiest part is using the computer. Any idiot should be able to wander in front of a computer, a calculator, the screen picture. Now, number 2, this is probably of the ones that I'm going to have you do, this is probably the hardest one. The person is going to go out and back, and out and back. And it's just like this. Don't turn around, it screws everything up. Okay? Do that back and forth, back and forth, back and forth. Mr. Groom, what's it going to look like? Displacement versus time. Assuming that this is 0 right here, probably going to look like this, isn't it? Give or take. What's your velocity going to look like on this one? What's the velocity like? What kind of velocity do we have here? Positive or negative? Positive. And then what do I have here? 0. And then here I have, so it's probably going to look something like this. Give or take.
It's a cosine.
Oh my God, it is a cosine. And calculus people. Sine-ish. Cosine-ish. You're like, wait a minute, is there like a relationship with derivatives and calculus? Yeah, there is. Yeah. And then acceleration will be similar. Sure, that's easy. And then it'll be a third one. Are you going to give us a paper? Of course I'm going to give you a paper. Chill, dog. I'll give it to you tomorrow. The third one is we're going to have constant acceleration. And this is the one I started to say was really hard. The other one, going back and forth, is not very hard. This is the hard one. It's really hard to walk with a constant acceleration. Now you're like, could I sprint with a constant? Maybe. Here's the problem. When you start accelerating constantly, how long does it take to get top speed for a human? Not very long. So it's going to be like, oh, and then I'm pretty much top speed.
I would cheat.
Right? And so that one you'll probably have to try 6 or 8 times to get it to work well. Now, as you know, I don't have a lab of sorts. So where can we go? On the commons? Sure. Can I go outside? Sure. Can we screw around wherever? No. No. Fusing? No. So you'll be out doing your thing. Be careful. In the past, it was bad because the motion detectors would pick up a bigger object. So some bigger person would walk behind you, and all of a sudden it starts tracking that person. It's creepy. Now the camera picks up everything, but you actually just track what you tell it to track, which again is sometimes easier said than done. Okay, so like tomorrow you're like, I'm gonna have to have it follow my shirt. That's cool as long as your shirt isn't basically the same beige color as the walls and the commons, and then it's gonna be tricky. Okay, nice red shirt or maybe a ginger head or what have you. I don't know. But you're going to try to find something that stands out. If it basically looks like the background, it's going to be really hard for the computer to figure out what it's looking at. Okay? So at some point later today, I'll have a video on my webpage that you can actually go and watch and follow along with, and it's going to be pretty cool. Now, before we leave, I'm going to show you something I put on my webpage the other day. First of all, I found this graph. It's amazing. It's pretty cool. And then I embedded it in my website. And so it's because I don't want to ever lose it. And knowing me. Look at this map. Look at this map. Load, you hippie. This map is a map of the entire world. But last week it was showing Hurricane Irma down here. Down here you see Hurricane Jose. Right here. See that low pressure system? Everything is going into the low pressure system. That's what's left of Irma right there. This right here is a low pressure. Everything's going into it. Here's what we call a saddle point. We'll talk about maybe that later on. Here is a high pressure system right here. This is a high pressure. Everything's coming out of it. It's generating here and coming out of it. There's a low right here. Everything's going into the low. So you can talk about the weather forecast. That's what it's about. But you can actually have it show right now. It's showing temperature. That's the color you see. You can show, you could show whatever, I don't know, air pressures. This is where the pressures are. Red's high pressure, blue is low pressures, and so on. Anyway, that was pretty cool, a little picture. We'll talk more about some of this stuff when we get to some weather stuff later on. Why aren't you doing anything? Anyway, whatever. Oh, here are the waves in the ocean, which direction they're blowing. By the way, if you follow the waves, they follow the wind. They follow the wind. So you see the winds blowing, you see the waves going the same directions. All right. Anyway, kind of fun, kind of interesting. Anyway, stuck it on there. It made me so happy. All right. That's all. Yes. No? Question?